Hello everyone, in this video, I'm going to show to you how to prove this theorem that n-1 times the ratio of sample variance over the population variance has a chi-square distribution with n-1 degrees of freedom. This n in here is the number of samples or the sample size. Now for this sample variance, we'll use this formula summation of x sub I minus x bar, which is the sample mean, squared from I equals 1 until n over n-1, where the x sub i's in here are the sample random variables. There are n of them. They are IID, means independent and identically distributed. That is, they are all independent to each other, and identically distributed. That is, they have the same distribution, a normal distribution having the same population mean mu and population variance sigma squared. Now for the sample mean, we'll use this formula summation of x sub I from I equals 1 to n over n. Now to prove this theorem, we're gonna use this theorem that the sum of the squares of these random variables, which has a standard normal distribution, has a chi-square distribution with degrees of freedom the same with the number of terms in here. So this is 1 until p. Now if you want a proof for this theorem, I have a video for this theorem and I provided the link in the description below so that you can check it out. Now to use this theorem, we need to convert the random variables in here, which is in terms of x sub I, which is a normal distribution, into a random variables, which has a standard normal distribution. To do that, we'll use the fact that x sub I, which has this distribution, minus mu, which is its population mean over its population standard deviation, has a standard normal distribution. Now, I believe that most of you understand this, but if some of you want a proof for this one, I will provide a proof for this one at the end of this video. After proving this using this fact, let us designate it with capital Z sub I. Then let us convert all x sub i's in here into in terms of z sub I. So we have now, for the sample variance, it is equal to summation of, for x sub I, we can have from here, x sub I is equal to sigma times z sub I. Then we can put this mu to that side, so we have here plus mu. Then we can use this one in place of x sub I in here, so we have here sigma z sub I plus mu, then minus our sample mean, which is this one. So let us convert the x sub i's in here, so we have here summation of, for x sub I we have this one, sigma z sub I plus mu, this is from I equals 1 until n, then over n. Then let us distribute this summation for each term here and also this over n. So we have here, since sigma is a constant, so we can have here sigma summation of z sub I from I equals 1 to n over n, then plus this mu is a constant, then summing it n times will be n times mu over n. Then we can cancel out this n in here and n in here. Then we know that this one is averaging z sub i's, so we can designate it as the sample mean in terms of z sub I. So we have here sigma times z bar, then plus mu, then this is squared, then this is from I equals 1 to n, so we have here I equals 1 to n, then over n-1. Then it is equal to, we can cancel out this plus mu and minus mu. Then we have a common term in here, sigma. We can collect it and move it outside of this parentheses, but we have squared in here, so this sigma will become sigma squared, And then since it is a constant, we can move it outside of this summation. So we have here sigma squared over n minus 1. Then summation of z sub I minus z bar. Then we have here squared from I equals 1 to n. Now we can move this one to that side by multiplying both sides by n minus 1 over sigma squared. So we have here n minus 1 times s squared over sigma squared. Then it is equal to this one. So we have here summation of z sub I minus z bar squared from I equals 1 until n. Now we can simplify it further by expanding this squared in here. So we have here summation of z sub I squared. So we have here z sub I squared minus 2 times this. So we have here 2 times z sub I times z bar, then plus z bar squared. This is from I equals 1 until n. Then we can distribute this summation for each term in here. So we have here summation of z sub I squared from I equals 1 until n, then minus this z bar is not affected by any value of I, so it becomes a constant for this summation. So we have 2 times z bar, then summation of z sub I from I equals 1 until n, then plus this z bar squared again is a constant for this summation, and it will be summed n times. So we have here n z bar squared. Now for this z bar, we know that it is the average of zi's to n over n. Then this one will be n times z bar. So this is n times z bar. Then this whole term in here will be 2 times n z bar times z bar is z bar squared. Then this is equal to this one, summation of z sub I squared from I equals 1 to n, then minus this one plus this one. We have a common term in here, this. So we have negative 2 plus 1 is negative n z bar squared. So we have now a simpler formula which is in terms of z sub I. Now if we compare this one with this one, they are the same. So what we're gonna do is to prove that that one has this distribution. So we're gonna prove this one has a chi-square distribution with n minus 1 degrees of freedom. Now you might think that why not check these terms in here if it has a standard normal distribution, since if this one has a standard normal distribution, then we will have here a summation of squares of random variables which has a standard normal distribution, and then using this theorem we can have a chi-square distribution. But this term in here doesn't have a standard normal distribution. We need some constants in here first, and even if this one has a standard normal distribution, then the resulting distribution in here will be chi-square distribution with n degrees of freedom, because we have n terms in here. Same with the number of terms in here. And what we're looking for in here should be a chi-square distribution with n minus 1 degrees of freedom. So in here it will still not prove our theorem. So now what we're going to do is to use the method of induction. in method of induction, we will have a base case and a inductive step. Now, for this base case, we need to find the minimum value of n such that our theorem is applicable. So in here, the number of degrees of freedom for a chi-square distribution should be at least 1. So n minus 1 should be greater than or equal to 1, or n is 1 plus 1 is greater than or equal to 2. So this is the minimum value for a value of n. So in here, we'll use a base case where n equals to 2. So for n equals 2, so we have here 2 minus 1 is 1, then s squared, let us put a subscript in here 2, meaning we are calculating the sample variance for first two samples, then over the population variance. From here, we will prove that this one has a chi-square distribution with n minus 1 or 2 minus 1 equals 1 degree of freedom. Then for inductive step, we will assume that when n is n equals 1, this theorem is true. Now let me copy this theorem below. So in here, n minus 1 is n minus 2. Then we have here sample variance for first n minus 1 samples, n minus 1 over sigma squared has a chi-square distribution with n minus 1 or n minus 2 degrees of freedom. Then after assuming this one, we need to prove that when n is equal to n, as this one, this theorem is true. So we have here, prove that n minus 1 times sample variance for n samples over sigma squared has a chi-square distribution with n minus 1 degrees of freedom. Now let us prove the base case. So we have here proof of base case. Now from here, when n equals 2, let us use this formula in here. We have n minus 1, which is 2 minus 1 equal to 1. So we have s squared over sigma squared. This is for first two samples is equal to, we have here summation of z sub I squared from I equals 1 until 2 only minus 2 times z bar squared, and this z bar should be the average of the values of the first two samples. So we have here 2 times z bar with subscript 2 squared. Then it is equal to, for I equals 1, we have z sub 1 squared, and then when I equals 2, we have plus z sub 2 squared, then minus 2 times the average of the first two samples, which is z sub 1 plus z sub 2 over 2, then we have squared. Then it is equal to, this one will become 4 because of this squared, and this one will become z sub 1 squared plus 2 times z sub 1 times z sub 2, then plus z sub 2 squared. Then we have here 2 over 4 or 1/2. So we have here z sub 1 squared minus 1/2 of z sub 1 squared is 1/2 of z sub 1 squared and then plus z sub 2 squared minus 1/2 of z sub 2 squared is 1/2 of z sub 2 squared, and then the remaining 1/2 of this one, which is just z sub 1 times z sub 2. Then we can extract 1/2 for each term in here, so we have here equal to 1/2 times z sub 1 squared, and then let me write this one first before this one. So extracting 1/2 for this one, we need to multiply it by 2, so that 2 over 2 is 1, which is this one 1, and then plus extracting 1/2 from this, we have z sub 2 squared, and then it is a perfect square, so we have here 1/2 z sub 1 minus z sub 2 squared, and then we can put this 1/2 inside this squared term, so we have here z sub 1 minus z sub 2 over square root of 2 squared, because if we square this one, we have here 1/2. Now in our base case, we need to prove that this one has chi-square distribution with 1 degree of freedom, and using our theorem, in here, if we have only one term in here, we will have a chi-square distribution with 1 degree of freedom. Remember this one, this z has standard normal distribution, so in here, if this one has a standard normal distribution, then this whole thing, which is this one, has a chi-square distribution with 1 degree of freedom, proving this one. Let us denote this inside in here as W. Then if W has a standard normal distribution, then W squared, using our theorem, has a chi-square distribution with 1 degree of freedom, proving our theorem. So now let us prove this to have a standard normal distribution. To prove this, we need to prove that the moment generating function for W is equal to the moment generating function for a standard normal distribution, because we know that two random variables which has the same moment generating function has the same distribution. For a moment generating function for a standard normal distribution, it is equal to e raised to t squared over 2. So we're gonna prove that this one is equal to this one. So let us do it now. The moment generating function for this one has a formula expectation of e raised to wt. Then it is equal to expectation of e raised to, for w, we have this. Now let me distribute this over square root of 2 for each term in here. So we have here z sub 1 over square root of 2 minus z sub 2 over square root of 2. Then we have here times t. Then we can distribute this t for each term here. Now we know from algebra that e raised to a plus b is equal to e raised to a times e raised to b. So this one can be rewritten as expectation of e raised to z sub 1 times, let us distribute this t for each term in here. So we have here t over square root of 2, and then times e raised to negative z sub 2 times t over square root of 2. This z sub 1 in here and z sub 2 in here are independent to each other because they come from here and x sub i's are independent to each other, the I in here. Then we know that if u and v are independent, then expectation of u times v is equal to expectation of u times expectation of v. That is, expectation of the product of u and v is equal to the product of their expectations. So we have here, we can distribute this expectation for each term in here. So we have here expectation of e raised to z sub 1 t over square root of 2, then expectation of e raised to z sub 2. Let me put this negative inside in here. We have negative t over square root of 2. Now this one has similar form with this one. If this z sub 1 is this w and this t over square root of 2 is this t in here, and also with this one, if z sub 2 is w in here and this term in here is t in here, then this is equal to homogeneating function for z sub 1. Then we have here t over square root of 2, then times homogeneating function for z sub 2 times this one, negative t over square root of 2. Then this z sub 1, remember that it has a standard normal distribution, and also this one, so we can use this formula, but using this for t in here and also this for t in here. So we have here e raised to t squared, which is square of this one, t squared over 2, and then over 2, so we have 1/2. Then e raised to square of this one, which is t squared over 2, then over 2, so we have here times 1/2. Then using this one will become this one. We will have here e raised to t squared over 4, and then plus this one, so we have here plus t squared over 4, or e raised to t squared over 4 plus t squared over 4, or t squared over 2. Now this one is the homogeneating function for this w, and since this one is equal to this one, then w has the same distribution with this z, which has a standard normal distribution. So this w has a standard normal distribution. So now, from here, it is true, then w squared, which is this one, and the same with this one, has a chi-squared distribution with 1 degree of freedom. So this one, which is same with this one, has a chi-squared distribution with 1 degree of freedom as proved. So now we have proved our base case. Now let us go with the inductive step. Let me copy this one, and then also let me copy the formula for this one. So we can assume this one, and then we can prove this one. This one has a chi-square distribution with n-2 degrees of freedom, while this one has a chi-square distribution with n-1 degrees of freedom. Now, to prove this, we need to use a theorem that a random variable which has a chi-square distribution with p degrees of freedom plus a random variable which has a chi-square distribution with q degrees of freedom has the same distribution with random variable which has a p plus q degrees of freedom, or we can write here has a chi-square distribution with p plus q degrees of freedom. Now in here we have a chi-square distribution with n-2 degrees of freedom. Let us write it this one, this one refers to this one, which we assume to be this one. And then if we add another one, which has a 1 degree of freedom, then n minus 2 plus 1 is n minus 1. We will have a chi-square distribution with n minus 1 degrees of freedom. So now, if this one can be expressed as sum of this one, which is this one, plus another one, which has a 1 degree of freedom, then we can prove that this one has a chi-square distribution with n minus 1 degrees of freedom. Now for the proof of this theorem, I have a video for this theorem, and I provided the link in the description below so that you can check it out. Now, what we want is n minus 1 n squared over sigma squared equal to this one sigma squared plus another term. So we need to find this one and then check if it has a chi-square distribution with 1 degree of freedom. So let us do it now. Is equal to, let us use this one. We have summation of z sub I squared from I equals 1 until n, and then minus n z bar. We need to put sub n in here for n samples, and then squared. And then we need to express to be the sum of this, and this is summation of z sub I squared from I equals 1 until n minus 1, and then minus n minus 1 z bar n minus 1 squared. So now we need to express first this one in terms of this one. So we can have here, we can extract the last term in here. So we can have here summation of z sub I squared from I equals 1 until n minus 1, and then plus z sub n squared. Then for this z bar sub n squared, we need to express it in terms of this one. So let us do it now. We know that z bar sub n is equal to summation of z sub I from I equals 1 until n, and then over n. And then we can extract the last term in here similar to this one, summation of z sub I from I equals 1 until n minus 1, then plus z sub n, and then we have here over n. And then we know that this one z bar sub n minus 1 is equal to this one over n minus 1, because we need here n minus 1 samples only. So we need to multiply this one by n minus 1 over n minus 1, so that it will become like this. We have an extra n minus 1 in here, so we have here, so this one over n minus 1 will become this one. We have here over n. Then we have extra n minus 1, and then this one over this one is z bar sub n minus 1, and then plus z sub n. Now for this one, we need to reduce it by this one, so we have here n times the square of this one, which is the square of this one, so we have here times 1 over n squared times the square of this one, which is, let us now evaluate, n minus 1 squared times this one z bar sub n minus 1 squared, and then plus 2 times the product of this, so we have here 2 times n minus 1 z bar n minus 1 times z sub n, and then plus square of this one, which is z sub n squared, and then it is equal to So we have here summation of z sub I squared from I equals 1 until n minus 1, and then minus, let us combine this one with this one in here. So let us write this first. So we have here n over n squared. We can cancel them out, but retain 1 over n. And then this 1 over n is n minus 1 squared over n, and then this z bar sub n minus 1 squared, and then minus of this one. So we have minus 2 times n minus 1 over n z bar n minus 1 times z sub n, and then plus this one minus 1 over n times this one. So we have here 1 minus 1 over n z sub n squared. And then we want to express this one in terms of this one, but this one has these terms, and for this term in here we have already that in here, but for this one we don't have yet. This is not n minus 1, but let us try to expand this one. So this term here will be n squared minus 2n plus 1, and then over n, equal to n squared over n is n, then minus 2n over n is 2, and then plus 1 over n. And then we're looking for n minus 1, so we can cut this into pieces, negative 1 minus 1. So we will have here summation of z sub I squared from I equals 1 until n minus 1, and then minus this n minus 1, then z bar n minus 1 squared, and then negative of negative 1 plus 1 over n, which is plus 1 minus 1 over n, and then z bar n minus 1 squared minus 2 times n minus 1 over n, then z bar n minus 1 z sub n, and then plus 1 minus 1 over n z sub n squared. So now we have this one, which is same with this one, so we can use this one in place of this one in there. So we can have here equal to n minus 2 s squared for n minus 1 over sigma squared, and then plus. Now for this one, this is n minus 1 over n, because n over n is 1, then minus 1 over n, which is same with this one, and also this one. This can be n minus 1 over n. Then we have a common term in here, this one, and this one. So we have here n minus 1 over n, and then the remaining are z bar n minus 1 squared minus 2 times z bar with n minus 1, then z sub n, and then plus z sub n squared. And then observe that it is a perfect square, so we have this one as z bar n minus 1 minus z sub n squared. Now what we are trying to prove that this one, which is same with below, is equal to this one plus a term which has a chi-square distribution with 1 degree of freedom. So we need to prove that these terms in here has a chi-square distribution with 1 degree of freedom. Similar to what we have done before, let me put this one inside of the square in here. So we have here n minus 1 raised to 1/2 over n raised to 1/2 times z bar n minus 1 minus z sub n. Then we have here squared, which is for this whole term. So we have this one. Now let us designate this one as W again. And if W has a standard normal distribution, then W squared, which is this whole thing, we are representing only W for this in here. This has a chi-square distribution with 1 degree of freedom. So if this one has a chi-square distribution with 1 degree of freedom, then we prove this one. So now let us determine the homogeneity function for W. This is equal to expectation of e raised to Wt Let me put it as small c. So we have here expectation of e raised to c times z bar n minus 1 and then minus z sub n times t. And then from algebra, e raised to a plus b is equal to e raised to a times e raised to b. So we have here expectation of e raised to, we can distribute this c and t for each term in here. So we have here z bar n minus 1 times ct and then e raised to z sub n times ct. Now this z bar sub n minus 1 has no z sub n because this one is averaging from 1 until n minus 1 samples. Now since z sub i's are independent, then this term in here and this term in here are independent. Since they are independent, then we can distribute these expectations for each term in here. So we have here expectation of e raised to z bar sub n minus 1 ct times expectation of e raised to z sub n ct. Now this one has similar form with homogeneity function formula, so this one will be a homogeneity function for z sub n, but instead of t it is ct. Then we know that the homogeneity function for standard normal distribution, it is equal to e raised to t squared over 2. So this one will become e raised to, so for t squared we need to square this one, so we have here c squared, t squared, and then over 2. For this one, let us put it in here. It is equal to expectation of e raised to z sub 1 plus z sub 2 plus z sub 3 plus etc. until z sub n minus 1 and then over n minus 1, and then we have times ct. And then we can distribute this ct over n minus 1 for each term here. And then let us use this one to have a product of exponentials. So we have here expectation of e raised to z sub 1 times ct over n minus 1 times e raised to z sub 2 times ct over n minus 1 and then e raised to z sub 3 times ct over n minus 1, etc. until e raised to z sub n minus 1 times ct over n minus 1. And then this z sub 1, z sub 2, z sub 3 until z sub n minus 1 are independent to each other. So these exponentials in here are all independent to each other. Then, similar to what we have done before, we can distribute this expectation for each term here. And then resulting in similar form like this, which is a moment generating function in terms of the random variables in here, but using this inside in here as t. So we have here moment generating function for z sub 1 at ct over n minus 1, then moment generating function for z sub 2 at ct over n minus 1, and then moment generating function for z sub 3 at ct over n minus 1, etc. until moment generating function for z sub n minus 1 at ct over n minus 1. And then since this z's in here has a standard normal distribution, then their moment generating functions are this one, but this t to be the term in here. So we have e raised to t squared, or e raised to t squared is square of this one, c squared t squared over n minus 1 squared, and then we have here over 2, so we have times 1 over 2. Now doing that in here, it will result in the same in here because this z sub 2, z sub 1 has the same distribution, which is a standard normal distribution. So this is same with this one until z sub n minus 1. So we are multiplying this one n minus 1 times, so we can put it as n minus 1. And then we know from algebra e raised to a and then b is equal to e raised to ab. So we can put this n minus 1 inside in here and then cancel out this squared in here because we have similar term in here. So we have here e raised to c squared over t squared over n minus 1 only times 1/2. So we have now this one, which is this one. So our moment generating function for w, we have this one, which is this one, and have this value. So we have here e raised to c squared t squared over n minus 1 times 1/2, and then times this one, which has this value. So we have here times e raised to c squared times t squared over 2. And then we can combine both exponentials. We have here e raised to, we have a common term, c squared t squared over 2. And then what is left in here is 1 over n minus 1, and in here is just 1. And then this one is 1 plus n minus 1 over n minus 1, because n minus 1 over n minus 1 is 1, and then we have here 1 over n minus 1 in here. Then we can cancel out this 1 and negative 1. So it will become e raised to c squared t squared over 2 times n over n minus 1. So now what is c squared? C squared is square of this one. This is c. So square of this one is n minus 1 over n. So this one is n minus 1 over n. And then multiplying it with this one, we can cancel out this n minus 1 and n minus 1. And then we have here equal to e raised to t squared over 2. Then it is the same with this one, meaning this W has the same distribution with Z, or has a standard normal distribution. So now we have proved that this W has a standard normal distribution. Then this whole thing will have a chi-square distribution with 1 degree of freedom. Then adding with a random variable which has a chi-square distribution with n-2 degrees of freedom will be a random variable which has a chi-square distribution with n-1 degrees of freedom. So now in using this theorem, this random variable in here and this random variable in here must be independent to each other. So we need to prove that this random variable in here and this random variable in here are independent to each other. So what we need to do is to prove that this expression in here and this whole expression in here are independent to each other. Now this sigma and n are constants, so this expression is a function of the standard deviation of the first n-1 samples. And then in here, it is a function of, so for z sub n, remember that we use the transformation function z sub I is equal to x sub I minus mu over sigma. So for z sub n, since this mu and sigma are constants, so it is a function of x sub n only. So we can put here, it is a function of x sub n. And then for this z bar sub n-1, this sigma and mu are constants, so this z bar is a function of x bar only. So we can put here x bar sub n-1. Now in here, this x sub n is a sample random variable for nth sample, while in here, this is a standard deviation and it is a function of first n-1 sample random variables only. Then it doesn't contain this x sub n. Since x sub i's are independent to each other, then this sample standard deviation for first n-1 sample is independent with this x sub n. So we should have no problem with the independence of this and this x sub n. But how about for this one? Are the sample standard deviation and the sample mean independent to each other? The answer is yes. So I'll write here the sample standard deviation and sample mean are independent to each other. Now if you want a proof for this, I have a video on how to prove this, and I provided the link in the description below so that you can check it out. Then now from here, this and this are independent to each other and this and this are independent to each other. Then their functions, which are this and this, should be independent to each other. So in above, this is the random variable y, which has a chi-square distribution with n-1 degrees of freedom, and this one is the random variable y, which also has a chi-square distribution with 1 degree of freedom. So from the argument below, this one and this one are independent. So it is okay to use this theorem. So now, based from this theorem, this one has a chi-square distribution with n-1 degrees of freedom, proving our inductive step. So we already proved this inductive step and this base case. Then we have proved our theorem that n-1 times the ratio of sample variance over the population variance has a chi-square distribution with n-1 degrees of freedom. So now for our appendix of this video, proving this, let me have another sheet. So in here, we're gonna prove that x sub I minus mu over sigma has a standard normal distribution where x sub I has a normal distribution with mean mu and variance sigma squared. The moment generating function for this one of t is equal to expectation of e raised to this one, so we have here, so we can distribute this sigma for each term in here, so we have here x sub I over sigma minus mu over sigma, then we have here t, then it is equal to, from algebra, e raised to a plus b is equal to e raised to a times e raised to b, so we have here expectation of e raised to x sub I times t over sigma, and then e raised to negative mu over sigma t. Now this one is a constant, so we can move it outside of this expectation, so we have here e raised to negative mu over sigma t times expectation of e raised to x sub I times t over sigma. Now this is a formula for a moment generating function with a x sub I random variable. We know for a normal distribution, has a moment generating function e raised to mu t plus sigma squared t squared over 2, and then it is equal to e raised to, let us use this t over sigma for t in here, so we have here mu times t over sigma, then plus sigma squared, then square of this one, t squared over sigma squared, then over 2. Then we can cancel out this sigma squared, and then this one will be equal to e raised to negative mu over sigma t times e raised to mu times t over sigma, and then plus t squared over 2. And then from here we can add the exponents, so we have here e raised to negative mu t over sigma, and then plus mu t over sigma, and then plus t squared over 2. Then we can cancel out this, so we have here e raised to t squared over 2. Now the moment generating function for a standard normal distribution is e raised to t squared over 2. So we have here z has a standard normal distribution, and since if two random variables have the same moment generating function, they have the same distribution, then x sub I minus mu over sigma has the same distribution with z, which has a standard normal distribution. So now we have proved that this one has a standard normal distribution. So that proves this one. This ends this video proving this. I hope you learned a lot from this video and to the next video as well. So thank you for watching, and don't forget to subscribe in my channel.